is not enough. You have your adaptive system. Everyone is adapting. Let's say 5 of you are adapting. But I take the information from 5 of you, but then I do
recollect some of the things that I have done. Okay. So what we had first was, we had matrices m by n real, and we generalize this give a transformation from Rn to Rm. And this preserved addition and scalar multiplication. There is a light here. Yeah. Okay. So the matrices gave us a transformation which converted n component vectors to m component vectors, and that preserved addition and multiplication. A of x plus y is ax plus ay, and a of alpha x is alpha ax. We then generalize this to the vector space situation. We replace these two by vector spaces and the matrix by a linear transformation. So then we had LVW, the collection of all linear transformations from V to W. VW are vector spaces over a field F. Okay. Then we looked at all linear transformations from V to W. These are transformations which preserve again addition and scalar multiplication. Any transformation which preserves addition and scalar multiplication is called a linear transformation, and we found that LVW is itself a vector space over F with usual addition and scalar multiplication. When I say usual addition, that means adding, how you add function. Linear transformations are functions, so how you add normally functions, how you multiply a function by a number. Okay. And what happens is that there is, in particular, if we take V equal to W, then we get LV. LVV is called LV, okay, instead of writing twice V. Now, any transformation with linear transformation which takes V to V is called a linear operator on V. So, it is the collection of all, is the vector space of all linear operators on V. Because this is a vector space, in particular if I put W equal to V, LV is also a vector space. When I have such a situation, this becomes also an algebra, because two operators can be multiplied, where the multiplication is thought of as the composition, okay, compose two transformation. So, LV has also multiplication defined as T1, T2. If T1 and T2 are linear operators, and then T1, T2 mapping V to V, the definition is, it takes any vector x as follows. First, T2 takes it to a vector in V, and then on that vector T1 acts. Okay. With this operation, then properties are multiplication distributes over plus, and we also have for any scalar alpha T1 T2 is the same as alpha T1 T2 is the same as T1 alpha T2. Whichever I do, you are going to same, like in matrix multiplication. If you want to multiply the product of a matrix by a number, you can take that number and multiply one of the matrices and then take the product. Same rule applies here. With these laws, it is what is known as a linear algebra. Okay. So what is the structure here? I have a vector space. On the vector space there is a multiplication, and that multiplication is distributive, and the scalar multiplication behaves nicely. Such a structure is called a linear algebra. So a vector space V over a field F, let me call it X, is called with an additional operation of multiplication is called a linear algebra if the multiplication obeys these laws, that is, it distributes over addition and both sides distribution T1 plus T2 into T3 is equal to T1 T3 plus T2 T3, both left distribution as well as right distribution, and that is this multiplication is distributive. And the second is that alpha T1 T2 is alpha T1 T2 is equal to T1 alpha T2 for all alpha in F. Okay. And of course T1 T2 are linear vectors. I should not even write T1 T2 here, probably I should write x1 x2, because do not think of them as transformations. X1 into x2 plus x3, let me put it this way, x1 x2 plus x1 x3, and then x1 plus x2 into x3 is x1 x3 plus x2 x3, and then alpha x1 x2 is alpha x1 into alpha into x2 is equal to x1 into alpha x2. So now I will write for every alpha in the field and for every x1, x2, x3 in the vector space X. Okay. So with this definition, LV becomes a linear algebra because it is a vector space. On that vector space we have multiplication, and the multiplication obeys this laws, and therefore LV is a linear algebra. And as I mentioned last time, linear algebra is the subject which studies the structure of such linear operators on a vector space. Okay, such linear algebra, study of the structure of such fellows. Okay. In particular, further, this algebra has an identity with respect to multiplication. Namely, the identity is the identity operator which takes every vector into itself. Identity I, that is with respect to multiplication. Let me put it this way, with respect to, that is I map V to V, Ix equal to X for every X in V, and Ti equal to It equal to T for every T in L. So it acts as the identity with respect to multiplication. So we call it a linear algebra with identity. Okay. So, it is a linear algebra. Therefore, LV is a linear algebra with identity. However, the product is not commutative now, because T1 T2 will be different from T2 T1, because just like in matrix theory, A1 A2 need not be the same as A2 A1. So, it is a non-commutative linear algebra. The product tells that it is a non-commutative linear algebra. It is not non-commutative. So, the LV is a non-commutative linear algebra with identity. Okay, so that was the first from matrices we generalized to linear operators, linear transformations and linear operators on vector spaces. Then we move to the next generalization. We have X and Y are nonlinear spaces. X and Y are nonlinear spaces, and first of all, since X and Y are vector spaces, all this can be done. So, therefore, since X and Y are vector spaces, basically I am completely reviewing what I did very quickly. Since X, Y are vector spaces, we have this LXY. Namely, the set of all linear transformations from X to Y, it is a linear algebra, okay, and in particular LX is a linear algebra with identity, and LX. The notions of LXY, and we also have the notion of LX, the set of all linear operators on X. LX is a linear algebra with identity, LXY is a linear algebra, okay, if X and Y are not equal. Okay. But then we said all this while we have been looking at only preserving the two fundamental operations in the vector space. But in the case of linear, in the nonlinear spaces, we have more structure. The norm brings in more structure. So, we would like functions which preserve these additional structures. So, in this context, we introduced two notions. One, namely a function from this vector space, this nonlinear space x to the next nonlinear space y is said to be continuous at a point x naught in x. The same story, if for every epsilon greater than 0 there exists a delta greater than 0, so that norm x minus x naught less than delta implies norm fx minus fx naught is less than epsilon. As I said last time, the norm here refers to the x space and the norm here refers to the y space. Okay. This is the same type of definition that we had in the real number situation, except now modulus is replaced by norm. Okay. Now, if it is continuous at all points, we simply say continuous. Okay. If f is continuous at all x not belonging to x, then we say f is continuous. We do not now have to mention it is a continuous map from x to y. Okay. Continuous function from x to y. Then we introduce the other notion of boundedness. Okay. So, f mapping x to y is said to be bounded there exists a constant m such that the transformed norm is under control compared to the original norm. Again, this is the y norm, that is the x norm. Okay. So, it cannot, the ratio of the changed length to the original length remains within a bound m. Okay. So, then we found a very nice thing, that when we are dealing with linear transformations, all these differences disappear. Okay. So, we said that if consider T mapping x to y a linear transformation, that is T belongs to Lxy, it is a linear transformation from x to y. And what we saw last time was, when this is so, continuity, boundedness and even continuity just at the origin all are equivalent. So, then we had this result, continuity, the following are equivalent. The following statements are all equivalent, that is any one of them will imply all the others. That is what is meant by saying the following statements are equivalent. 1, T is continuous. 2, T is continuous at the origin, just at that one point. So, when I say these two are now equivalent, if it is continuous at this one point origin, it is continuous at all points. That is the beauty of a linear transformation. And 3, T is bounded. So, all these statements are equivalent. So, any one of them I will mention. Usually I will say bounded. Okay. So, therefore, we have to only look at bounded linear transformation, which is the one that preserves a certain important structure coming out of this norm. So, we denote by Bxy the collection of all bounded linear transformations from x to y, from this nonlinear space to this nonlinear space, and in particular if x equal to y, we get the collection of all bounded linear operators on x. And so, we by Bx we mean the collection of all bounded linear operators on x. Okay. So, that is the special case where the domain and the codomain are the same. Okay. So, studying bounded linear operators is like studying square matrices, and studying bounded linear transformations is studying general rectangular matrices. The generalizations will be towards that, but you will find there are lots of hurdles if the space becomes infinite dimensional. Okay. We just cannot carry over everything that we did in matrix theory. There is a class of things for which we can carry over what everything we did with matrix theory. Okay. So, what is the situation now? Let me first make this comment. So, we have this is Lxy. This is the collection of all linear transformations from x to y. Now, these bounded linear transformations are linear transformation with additional property. So, there is going to be In general, this will be the situation. So, from the very terminology that these are linear transformation with additional property, we get that this is always contained in Lxy. And the counterpart, if x is equal to y, this will be always contained in Lx. Okay. The set of all bounded linear operators is a subclass of the set of all linear operators on x. The set of all bounded linear transformations from x to y is a subclass of the collection of all linear operators on linear transformations from x to y. The very in all infinite dimensional cases you have a problem that there will be something here, things which are not bounded, but in finite dimensional spaces we will see later these two collapse into the same. Okay. In finite dimensional spaces, therefore, we will see later that these two collapse, which means that whatever properties we demanded that the transformation preserve because of the norm being there are automatically taken care of by the fact that they are already linear. Okay. Nothing new comes out by demanding that the norm properties be preserved, okay, the topology be preserved. Linear transformations on finite dimensional spaces will automatically preserve the topological requirements that we are asking for. But in infinite dimensional space there will be a gap. There will be linear transformations which will not be bounded. Okay. So, let us make that comment first, remark. In general, we may not have bxy equal to Lxy, or in the special case bx equal to Lx. We may not have bx equal to Lx. If we show this, that means automatically this, we are taking y equal to x. So, in general this may not be true. Let me give you a very simple example. For example, so I am going to construct an x, I am going to take the same x as y also. Okay. The x is very simple, namely consider all continuous functions. Okay. We are not going to take all of them anyway. On this, they form a vector space, right. On that we have a norm, continuous function, say on an interval 0, 1. We have the maximum norm. The norm of f is defined as maximum of fx. If we have a continuous function on a closed bounded interval, it will have maximum, and therefore we can take the maximum modulus of the thing as the norm. Now, I am not even going to take that. Inside that there is sitting a smaller group of functions, namely polynomial functions, which are all continuous functions, but in addition they are also polynomials. So, I am going to look at, let me use some notation, P R 0 1. What it means? They are polynomial functions with real coefficients and for the variable x between 0 and 1. So, this is the set of all Px equal to a naught plus ak Px such that Px is a polynomial and 0 less than or equal to x less than or equal to 1. So, I am going to look at only functions which are polynomial functions and for the variable x between 0 and 1. I am not even worried about the variable x being outside 1. Okay. Now, any polynomial function is continuous, so it is bounded, it has maximum. So, we define norm P infinity to be the maximum of Px as x varies between 0 and 1. Okay. So, that is a norm. With that norm, this becomes a normed linear space. Okay. So, these two together give us a nonlinear space and we call that X. Okay. So, we have a nonlinear space X norm infinity. I will just call it norm. This is X, so this is my X, so that is X and this is the norm. So, I have the X and the norm, so I got a norm linear space. It is a linear space because sum of two polynomials is a polynomial and so on and so forth. There is no problem about that. So, now let us look at something very simple here. Just to understand this, let us take the polynomial p n x to be x to the power of n. Certainly this is in where n is 0 or 1 or 2 or 3 whatever it is, n is a non-negative integer. This is certainly belongs to the space. What is the norm of Pn? The maximum of x to the power of n in 0 1, which is obviously 1. So, the norm of Pn is all 1 for any n. So, for n equal to 0, 1, 2, 3 etc., we have this. Okay. The norm of Pn is 1. Very simple. That means they are all unit vectors. Okay. They are all unit vectors in that space. Right. Now, define a transformation T from x to x as T of P is the derivative of P. Well, if I differentiate a polynomial, I still get a polynomial. So, therefore, it is certainly a transformation from x to x. It converts polynomials to polynomials. And again, differentiation is linear operator. The derivative of a sum is the sum of a derivative and constants can be pulled. Therefore, it is a linear operator. Okay. Clearly, T is a linear operator on x. So, we have therefore T belongs to Lx, which is a linear operator and therefore it belongs to x. Now, we will see that this is not bounded. This is not a bounded operator. See, what is T of Pn? T of Pn is n x to the power of n minus 1. I am differentiating that. Okay. So, therefore, what is norm of Tpn? That will be the norm of this, the maximum of this, which is n. So, therefore, as I go on increasing n, this will go on increasing. So, there is no way I can control the transform norm. So, let me write it very carefully. So, norm of Tpn is equal to n into 1, which is n into norm Pn. So, I can't put any m there such that norm Tx is less than or equal to m times norm x. Whatever m I put, there is one Pn which goes beyond that. Okay. So, therefore, and as n goes to infinity, we see that norm Tpn goes to infinity and therefore, there does not exist m such that Tp is less than or equal to m times norm P for all P. There cannot be any such m. Therefore, T is not bounded. T is not bounded. So, it is a linear operator, it is not bounded. So, T does not belong to V of x. So, therefore, we have something in the gap now. This is this and this is the bounded thing, this fellow lives outside. So, therefore, we have Bx is strictly contained but not equal to Lx in this case. So therefore, the class of bounded linear operators in general is much smaller class than the class of all linear operators. So the class of all bounded linear transformations from x to y is much smaller class than the set of all linear transformations from x to in general. Okay. Right. So that makes things that there are strange things that are going to happen, and this happened because we could get infinite number of vectors which have norm 1 and which behave crazily. Okay. All of them are linearly independent in that space. So the space is infinite dimensional, and therefore all kinds of crazy things happen. Okay. So infinite dimensional spaces will give you lot of surprises. Okay. Okay. So that's example is just to warn you that there are some strange things that are going to happen in infinite dimensional spaces. Okay. So now let's get back to therefore this studying these bounded linear transformations is going to be probably a better thing. Study things which are better behaved first, and they may give you some clue. Okay. These are fellows which have some preservation of all the structure that is available to us. Okay. So now let's make certain comments about bounded transformations, because we will be using in all formats that property. So what is meant by a bounded transformation? So suppose T is a bounded linear transformation from x to y. What is the definition of this? Therefore, there exists an M such that norm Tx is less than or equal to M times norm x for every x in x. That is the definition of a bounded linear transformation. So of course it is linear, and in particular because it is bounded, there must exist a constant such that these transformed lengths are under control. So we can write it as norm Tx divided by norm x is less than or equal to M. Of course, since I am dividing by x, I must say x is not 0 for all x implies for every x not equal to the 0 vector. So the ratio, this is the elastic limit, the ratio of the new length to the old length is under control. It will not be more than M. So we are working within an elastic limit of M. That's what it really means. Okay, the strain. Okay. Now let us look at this ratio. What is this ratio? This is a number. What sort of a number? Non-negative number, because the norm of anything is always a real number greater than or equal to 0. So numerator is a non-negative real number. So the denominator is a non-negative real number. So the ratio is going to be non-negative. So they are greater than or equal to 0. So they are bounded below. Okay, they have to be on this side. And what this says is this is also bounded above. Okay, so therefore this as x belongs to x and x does not is a set of real numbers which is bounded above. I am interested in the bounded above from here, okay, because that ratio is bounded above. But whenever you have a set of real numbers which is bounded above, it should have a least upper bound. Okay, the real number says every bounded set has a least upper bound, or whatever you call it, supremum. So therefore this set of numbers must have a least upper bound. M may not be the least upper bound, maybe something even smaller works. We want to push this to the limit and see what is the smallest bound that works. So therefore this set has a, therefore has a least upper bound or what is known as the supremum. I will use from now on the word supremum, what's formally used. Okay. So therefore, the supremum of norm Tx by norm x, x belonging to x, x naught equal to theta x, that number exists as a real number, real positive number. Okay. That number exists, and that number is denoted by, so this is notation, that number is denoted as norm T for whatever reason. We will see why. That number is denoted by norm T. See, that number involves everything. Sorry, I think this is some problem. That number involves the denominator. What norm we are talking about? The x norm. The little x corresponds to the norm in the space x. The numerator involves the norm in the space y, and it also involves the transformation t. So it involves both the spaces, both the norms and the transformation. And once we fix the two spaces, the two norms are fixed and it is connected with the transformation t. But in defining that number, both the norms play a role. It is not that only one norm plays the role. So if I keep the same x and change the norm in y, keep the same transformation, then norm t will change. If I try to change any one of them, things may change. Okay, so this number is denoted by norm t. Okay, so this is a notation. So there are few things that we are going to observe. Okay. I will make a couple of lines here. I will leave it for you to verify. Instead of this, suppose I take this and put it as x by norm x, what I get? Because the norm x is a number that can be pushed inside and it will become t of x by norm x. X by norm x is a unit vector. So it basically boils down to, instead of looking everywhere, look at only on the unit sphere and look at what is happening on the unit sphere, how it is changing, and that will tell you how everywhere else it is changing. Okay, what is the elastic limit? So that is, it can be written like this, or it can also be written as, you look at the entire ball, unit ball, and look at the ratio, and that will still be norm 2x by norm x now. That will still be norm t. So the norm t can be written in many ways. You can look at only the unit ball changing, unit sphere changes in the unit sphere, or changes in the unit ball, or changes everywhere else. Depending on whatever you see, whichever you focus, you are going to get the same number, norm t. So with this in mind, we have already used the terminology norm t in anticipation that it is going to be a norm. Okay, so first thing that we observe is the following. Suppose T1 and T2 are bounded linear transformations from x to y. Okay. Suppose T1 and T2 are bounded linear transformations from x to y. So what is meant by saying that T1, okay, by the way, what can we write here? Norm Tx from now on can be written as norm T into norm x for every x in x, because that is the smallest bound we can think of. Put that there and multiply it. Okay, that ratio, the maximum value is norm term, so therefore that follows. And we have done x not equal to 0, but if x is equal to 0, it is obvious. Okay, so that's we don't. So now suppose I have two bounded linear operators. Okay, then for this there must exist a constant. So, norm T1x is less than or equal to norm T1 into norm x for every x in x, and norm T2x is less than or equal to norm T2 into norm x for every x. Okay. So, now look at the sum. If I now look at the sum operator, by definition the sum is defined as T1x, the sum of the two transformations defined as T1x plus T2x, but now this is a vector in y, this is also a vector in y, then we can apply the triangle inequality for the norm in y. So, that will be less than or equal to norm of T1x plus norm of T2x. It is simply the triangle inequality for the norm in the space y. But now I have norm of T1x is this, norm of T2x is this. So, this is norm of T1 plus norm of T2 into norm of x, or T1 plus T2 into x norm is less than or equal to some m times norm x, where m is norm T1 plus norm T2. So, what does that tell about the sum operator? That is also a bounded linear operator. So, the sum of two bounded linear operators is also a bounded linear operator. So, we get therefore, this implies T1 plus T2 belongs to Bxy. Not only that, and the norm of T1 plus T2 must be less than or equal to this constant. This is one of the constants, but the smallest constant is called the norm. So, that is less than or equal to norm T1 plus norm T2. This is one of the bounds. The least upper bound is called the norm. So, that is less than or equal to. Therefore, it is not only that the sum of two bounded linear operators is also a bounded linear operator, but the norms is also maintains the triangle inequality. Similarly, the next one is easy to verify. Similarly, alpha belongs to F, where alpha F is real or complex. Whenever we are dealing with nonlinear spaces, we decide whether we work on real nonlinear spaces or complex nonlinear spaces. The norm of T belongs to Bxy implies alpha T belongs to Bxy, and the norm of alpha T is equal to mod alpha into norm. This is therefore the notation was in anticipation used that this is going to satisfy the properties of the norm. Okay. So, what does this say? This says alpha T is also a bounded linear transform. So, what is the conclusion? Bxy is a vector space. It is sitting in the bigger vector space called Lxy. Bxy is a subset of the bigger vector space Lxy, and it is closed under addition under scalar multiplication, and therefore it should be a subspace. So, the set of all bounded linear operators form a subspace of the set of all bounded linear transformations form a subspace of the set of all linear transformations. Okay. So, therefore, hence Bxy is a subspace of Lxy. And because it is subspace, it is a vector space. Every subspace is automatically a vector space, and now I have a norm on that vector space. Why is that a norm? Already triangle inequality and this are there, and it is greater than or equal to 0. and it is 0 if and only if Tx is 0 for all x, that is the 0 operator. So automatically therefore that is a norm. Further, norm T as defined above is a norm on Bx. Therefore, Bxy is a non-linear space over F. So, if X and Y are non-linear spaces, the set of all bounded linear transformations from X to Y is also a non-linear space with respect to the norm which is induced by both these norms and the transformation. In defining the norm of the transformation, we invoke the norm of the domain space as well as the domain of the codomain space, norm in the codomain space. So the norm of the transformation is induced by the two underlying norms. Okay. So Bxy becomes a normed linear space on its own right. Okay. So now we have this Lxy, which was only it had the vector space structure, but inside that I have a subspace which is not only the vector space structure but also the nonlinear space structure. So the Bxy is a much more nicer structure that it has the norm because it was obtained from the fact that it also preserved the normed properties of these two spaces, and that made this also a non-linear space. In particular, if I take x equal to y, Bx therefore is a non-linear space, and Bx also has a product, right? When I have Bx, I can take the product of two linear operators, that is also a linear operator, and it turns out very easy to verify that the product of two bounded linear operators is also a bounded linear operator. Okay. Bx is a non-linear space, and if T1, T2 belongs to Bx, then for every x in X, norm of T1, T2 X is equal to norm, what is the definition? T1, T2x is defined as T1 of T2 of x. This is T1 of some y. T1 of some y is always less than or equal to the norm of T1 into the norm of the y, because T1 is bounded operator, right? T1 of z is less than or equal to norm T1 into norm z. So I am taking this as z. Now I apply that T2 is also bounded, so this is less than or equal to norm T1 into norm T2 into norm x, and therefore norm T1 T2 x is less than or equal to k times norm x, which is this is k. And what does that tell about T1 T2? That is a bounded linear transformation. So T1 T2 belongs to Bx, and norm of T1 T2 will be less than or equal to the product, because that is one of the bounds. The smallest bound is called the norm. So that's it. So this is not only a non-linear space, it is also an algebra. In that algebra, this norm property is maintained. So we call it a normed linear algebra. So Bx becomes a normed linear algebra, and it has identity also, because identity is a bounded linear, its norm is 1. No change is taken place. Norm of Tx by norm of x is norm of x by norm of x, the norm of I becomes 1. Okay. So therefore this is a normed linear algebra with identity. So Bx is a normed linear algebra with identity. Okay. I always have a complaint with some of my friends in the mathematical world. You see, analysis started very nicely. Analysis started with the nice marriage of algebra and topology, and we had all this norm giving us all topological notions, vector spaces giving us all these notions, and then we are looking at various things like operators, which were generalization of matrices, and so we looked at similarly equations corresponding to operators. A lot of nice things were going on. Integral operator theory developed beautifully. Then this business of algebras came. The moment these algebras smell algebra, they take it off in the direction of algebra, okay, and the analysis is lost. It lost in the sense that the route from which it started, somewhere or other the connection is getting slower and slower, remote. Okay, the fact that we started from matrices and we want to keep that is the thing ideal for us for solving equation systems, etc. And that part generalized to integral operators and other functional equations. That part was lost, and all kinds of algebras of operators are studied. And up to some stage, like the compact operators, normal operators, these algebras were very nice, but beyond that, even to construct one example for what they are studying, concrete example becomes extremely difficult. And if you cannot have a concrete example, that means we are still not seeing its connection with reality. Okay, so they are all very abstract. So they go to, so this is what I don't know, once there is a famous saying, I don't remember who said it, that geometry was a beautiful subject, and there came a stage sometime in the second half of the 19th century, geometry was getting more and more algebraized. Okay, so algebra basically took over geometry. Okay, and then somebody described this as the devil taking over the angel. Okay, see, the algebra is taking over geometry was like the devil taking over the angel. Geometry was the angel, algebra was the devil. Okay, somehow or the other, these algebra is I hope there is no algebra here. These algebra is are some people. I knew a very famous, very well-known mathematical physicist at the Brookhaven National Lab. He used to call these algebras themselves as devils. Okay, so the moment they come in, we lose track of reality. We run for life, our life. Okay, and once they enter, what they see is only algebra. They refuse to see anything else. Algebra, algebra, and algebra. So I have people, I tease sometimes I make lot of enemies particularly among Indian mathematicians. I say that in India there is a large group which controls all the money for mathematics, which feels only algebra, algebraic geometry, algebraic topology, algebraic number theory, anything algebraic blah blah is mathematics. Nothing else is mathematics. So we will not give money, and that's the unfortunate situation. Anyway, this is what happens sometimes when you try to see things not in holistic manner, but in isolated things. So, but in my opinion, mathematics is very holistic. Analysis is one subject which looks at things, everything, geometry, the orthogonality, everything into the picture, and looks at the problem in a holistic manner. Okay. Anyway, we will not be going to the level where the devil takes over. We will stop short of it. Okay. Because I don't want to trot into the devil's territories. Okay. Okay. So now therefore we have that the Bx, the class of all linear operators on a nonlinear space is a vector space. It's a subspace of the vector space of linear transformations from x to y, and it is a non-linear space, and in particular if I take x equal to y, the collection of all bounded linear operators and non-linear space is a linear space, is a non-linear space, is a non-linear space with identity, it's a non-linear algebra. Okay, all nice things that you want. You can do addition, multiplication, matrices multiplication, corresponding thing is there, identity there is, corresponding thing is there, and of course matrix itself is not commutative in multiplication, so it is too much to expect that it will happen. And geometrically it's a composition of two transformations is never commutative, so but you can't expect it anyway. Right. So now I am going to specialize this. Let me make one or two remarks. Okay, all right. So I will make sort of an outline of what we are up to. Okay. So now Bxy is a nonlinear space. Okay. That we have seen. So if X is a nonlinear space, Y is a nonlinear space, the set of all bounded linear transformations from X to Y with that induced norm is a nonlinear space. The moment I have a nonlinear space, immediately ask, is it complete? Whenever I have a metric space, I ask, is it complete? Every nonlinear space, it's metric space, so I ask whether it's a complete. And a complete nonlinear space is called a Banach space. So I want to know whether this is a Banach space. So is this a Banach space? Question 1. Is Bxy, and similar questions will be asked when x is equal to y. Okay, we can take x is equal to y and look at operators also. Is Bxy complete? That is Bxy a Banach space? I will give the answer to this. We will look at the details of the answer later. The answer to this question is probably, somebody may think the X was not a Banach space, we said only nonlinear space. Why we did not take it as a Banach space, we took it only as a nonlinear space. Then why do we even expect that Bxy will be a Banach space? Maybe we should ask both X and Y first of all to be Banach spaces, then ask whether Bxy is going to be a Banach space. But it turns out, irrelevant of whether X is a Banach space or not, as long as Y is a Banach space, Bxy will always be a Banach space. So Bxy is a Banach space if Y is a Banach space irrespective of whether X is a Banach space or not. Okay. So whether X is a Banach space or not, as long as the codomain is a Banach space, as long as the codomain is, see, remember now this codomain is going to play a role. We will see that there are certain things that if it is happening in the codomain, nice things are happening. Because finally T is going to go there. If you are going to end up in a ditch, definitely you are going to get dirty. But if you are going to end up in a nice place, like came to IISc, your future is guaranteed. Okay, nice things are going to happen. So where you are landing is important. Okay, so therefore it's the Y that is going to make things nice. Okay, under this transformation. So whether X is a Banach space or not, as long as Y is a Banach space, then Bxy will be automatically a Banach space. Okay, so that is the first result which we will prove. Okay, these are all fundamental results. So these things at least I will give a proof. Now, what is the consequence? There is a very, very important consequence of this. So, that is what the beginning of functional analysis is an important consequence. Take a nonlinear space. Over F, where this F is what? Real or complex. So, I always consider either real nonlinear space or complex nonlinear space. Then suppose F is real. Let us take for example F is real. If F is real, I can take Y to be R itself. Real numbers form a nonlinear space, right? I can take R to be Y to be R. Or if F is C, I can take Y to be C itself, and the complex numbers is a complete nonlinear space. So, if I take Y to be F, remember Y is equal to R or C, and with the usual norm Y is a Banach space. The real numbers form a complete space, the complex number form a complete space. So, Y is a Banach space. So, therefore, the set of all bounded linear transformation from X to F must be a Banach space, because Y is given to be a Banach space. So, F is a Banach space. So, Y is a Banach space, and therefore, BXF is a Banach space. So, what is meant by BXF? It is linear transformation. It transforms every vector to a number. The Y space is now a number. Every vector is transformed into a number, and this transformation is such that that elastic thing is maintained. Then the collection of all these transformations, such transformations becomes a Banach space. Such transformations are called bounded linear functionals. If the codomain is the number thing, scalars, then it is called a functional. So, these are called, so if F belongs to BXF, we say F is a bounded linear functional on X, and we denote the collection of all bounded linear functionals by X star. Bounded linear functionals as X star, and this is called the algebraic dual of, topological dual of X. So, called topological dual of X. Okay. So, let me make so what does that mean? Suppose F belongs to X star, what all we mean? That means F is a function from X to the field. With each vector it associates a number. 2, F is linear. What does that mean? F of X plus Y is F of X plus F of Y, and F of alpha X is equal to alpha F of X. That is what is meant by linear. Okay. Then it is bounded. What does that mean? There exists an M greater than or equal to 0 such that norm of f of x. What is the norm? F of x is in here. So, what is the norm here? It is just the modulus. It is a real or complex number. So, mod f of x is less than or equal to m times norm x for every x in x. And how do we define the norm of the transformation? It is defined as the supremum x not equal to theta x, x belonging to x, of norm of fx, but that is S mod fx by norm x. This is what the norm of the functional is. The y norm is just now a modulus because they are all numbers. This is what we mean by when f belongs to x star. And what we have seen is whatever be x, as long as it is a nonlinear space, this is a Banach space, and therefore by the answer to the question 1, x star is always a Banach space. Okay, that's a nice thing. Okay, x star is a Banach space for all nonlinear spaces x. For all nonlinear spaces, the dual is a Banach space. Okay, so now let me conclude by making one statement. So first we have Lxy, then we have Bxy. Okay. Correspondingly, if we take y equal to f, take y equal to the field of scalars, real or complex, then we have L x f, and we have this B x f, which I call as x star. Okay. Now this is called, this portion, whatever is here is called the topological dual, and whatever is here, that is denoted by x prime, and that is called the algebraic dual. So in general, the topological dual is smaller than the algebraic dual, because there we don't do any continuity or anything like that. We are looking only x and y as vector spaces, and we are looking at all things which associate a number with every vector. So what we are doing is, we are coding every vector as a number, or we are extracting a number connected with every vector. Okay, so in other words, we are trying to extract some essence out of that every vector, and this is what the beginning of trying to digitalize. Okay, so we want to collect some more functionals, and so for each functional we extract a number of this signal, and now knowing these numbers, can I make statements about the original vector? That is, I can store only these numbers, and that's enough for me. I will extract information about the vector. So that's precisely what functional analysis is. What are the right type of functionals which control the nonlinear space? Okay. And that is one thing, that the functional analyst may be satisfied with that. Okay, I tell you, if this is the nonlinear space, this is usually the nonlinear space that we consider are function spaces, certain type of function signals. It may be one dimensional or two dimensional or whatever it is, certain function spaces we are going to consider. So with these functions we are going to extract some numbers, and from these numbers we want to make predictions about that function. Now the mathematician says, I will tell you which functionals, but however a practical man will say, okay, that's fine, but how difficult is it to extract these numbers? If extracting these numbers is difficult, then this whole process of digitalizing is difficult. That is one thing. The second thing is, okay, the extraction is easy, but having extracted, to reconstruct that other fellow, if that is going to be difficult, again your thing is useless. Okay. So therefore now what is meant by difficult, easy, etc. is what the engineer says, how complex the algorithm is, time wise, computation wise, and consumption of energy wise. Okay, suppose I take this signal, I want to extract the numbers, I want to extract as few numbers as possible because I want to transmit them, and the energy battery I have is very small. Say I am sending it from space, then I want to send as minimal information as possible. From that it may take a long time to reconstruct the original, but who the hell cares? The ground staff can take their own time to reconstruct. Or the other way around, I am producing a music CD, then there is only one time extraction that is there. I may take a lot of time, but everybody is going to play that CD. Cannot wait eternally for the CD to reconstruct the signal, and then so therefore there I want the other way around. The fellow reconstructing must be quick. It doesn't matter your extraction takes a long time. You extract and then put it and then give me the CD. So every problem has its own very peculiar requirements. Okay, so mathematically we must say, okay, there are these functionals that decide, and that is why this search for basis goes on and on and on, which is the right basis for which purpose, and it is never ending. Okay, we had first of all Taylor, that was only local, then came Fourier, that was only periodic, then came Fourier transform, that was only for band limited signals, and one of them was local, the other one was global. Is there some way of doing both local and global together? People thought of wavelets, and wavelets the known were bad. Then they asked, can we do compact supported wavelets? Then came Debussy and showed how to construct, and still the search is which wavelet is suitable for which problem. All this is still not settled. It goes on and on, but the fundamental idea is what these functionals are. So, okay, so the functionals play the key role in all this analysis, and therefore functional analysis is going to be a very important subject in all this. Okay, so you will see that if you see Debussy's 10 lectures on wavelets, you will see a lot of functional analysis, particularly with respect to a particular Banach space, which is also so-called Hilbert space, namely the L2 spaces. Okay, all the signals are assumed to be finite energy, and therefore this L2 space comes into the picture. So basically, therefore, what I want to say is these functionals are at the foundation of all these analysis, and that is why the name functional analysis. Knowing these numbers, what can I say about the function? What are the right numbers to know, and so on. Therefore, for every x, there are certain codes which arise out of these functions. Each functional gives a code to that x as a number. So now I want to collect the right codes and keep it with me so that I can get that fellow whenever I want. One f will not work because it's going to give you only one information, or you may even look at it as in a sense that we are doing some kind of huge amount of information which you are going to plow and get like the Google does. Then what is the f which gives the best information first? Okay, then we can layer the information, the second layer and the third layer and all, and that belongs to the eigenvalue problems. Okay, the right matrix constructed, the largest eigenvalue and the next largest eigenvalue, and then the corresponding coefficients corresponding to that vector. This is the essence that we are going to extract. So basically almost all the problems, a large class of problem, boil down to studying the right type of functionals, and basically everything is going to be bounded functional, otherwise the analysis is going to be difficult. So the x star is the key. Okay, so I will give a number of examples of this x star so that we understand what x star is. So next time I will take that question 1 and give the answer, give the proof for the answer, that when y is a Banach space, bxy will always be a Banach space. In particular, bxf is a Banach space, and so we will give examples of this x star. Okay, all the standard known spaces, most of them, the X star is very nicely identified. Okay, it behaves nicely. Okay, so we will see finally, therefore, even the business of delta, it gets a proper meaning as a functional and not as a function, the Dirac delta. Okay, this functional is the key. Okay, the functional, what it does is, whatever is your vector, whether it's a function, whether it's a matrix, whatever it is, as long as you have vector space, it extracts a number for every one of these vectors. Okay, that's what a functional does. It's linear if superpositions are preserved. If it's bounded, if it works within certain elastic limits. That's all that matters. Okay, so that's where I stop, and next time I'll continue from here.